Hi everyone, I'm Sreeraj Rajindran. I'm a PhD candidate at the University of Technology, Sydney, and I did this work as part of the internship at Dolby Labs, Sydney. The title of our work is Short-Time Quantum Fourier Transform Processing. The co-authors of this paper are Ben Southwell of Dolby Labs and my own academic supervisor, Ferrie of UTS. Now we come to the core of our work. The proposed project was to employ quantum windowing in conjunction with quantum adapted version of classical signal reconstruction algorithm and to demonstrate quantum speed of advantage, if any. Why is it important? What's the motivation behind our work? Successful use of quantum algorithms for signal processing will require this sort of or some uh, reconstruction algorithm similar to the one we propose. Rolling codec in conjunction with quantum algorithms will need this as a subroutine somewhere down the line. And the novelty of our project is this. Quantum windowing is a relatively less developed aspect of quantum signal processing. It is crucial to bridge this gap in research. Reconstruction has never been attempted with quantum window Fourier transform. That's the motivation and novelty why we decided to work on this project. Our objective was to adapt the classical reconstruction framework to the quantum domain. An example of a classical reconstruction framework is short-time Fourier transform (STFT). In STFT, we window a large signal, we process the large signal in the Fourier domain, and the various windowed outputs are stitched back together using a reconstruction algorithm such as overlap add. Our proposed framework is twofold. The first aspect is to adapt the windowing and the processing in the frequency domain, which we call QWFT, which stands for Quantum Windowed Fourier Transform. And once we have the windowed processed outputs, we have a secondary algorithm, which is the quantum reconstruction algorithm. We have designed a quantum overlap add, which stitches back together those windowed outputs to have a coherent, continuous signal at the end. So what is a quantum state as defined in quantum information? Well, it's just a column vector from linear algebra. There are two conditions that the column vector should satisfy. The first is that the entries of the vector are complex numbers, and the second is that the sum of the absolute values squared of the entries must equal to 1. That's it, that's the quantum state. And the Euclidean norm is defined as seen on screen. Quantum state vectors are therefore unit vectors with respect to this norm. As you can see, the way this column vector grows is as a power of 2. So if we have a 1 qubit quantum state, then it's a 2 to the 1 column vector. If we have a 2 qubit quantum state, it's 2 to the 2 squared size column vector. How is the quantum window state prepared? For that, we actually perform element-wise multiplication, L2 normalization, and padding to a power of 2 in the classical domain, which we label as classical preprocessing. Thereafter, these classically processed data points are actually amplitude encoded as coefficients of the column vector, which is the stand-in for the quantum state. This is the quantum processing, and thereafter we go into the quantum circuit. Let's talk about our first subroutine, where we encode the filter as a quantum register. Just as we amplitude encoded our windowed signal into a windowed state, we amplitude encode our filter, in this case a boxcar filter or an averaging filter or any other filter for that matter. We also track the filter norm as we did earlier for window norm. And once we have the windowed state and the filter as quantum states, we perform QFT, which is quantum Fourier transform, to bring it into the frequency domain. Once that's done, obviously to perform a quantum convolution, we just have to perform an element-wise product in the frequency domain, which is done in the manner shown here. These are in the middle are called as controlled NOT gates, and once that's done, we perform inverse quantum Fourier transform to get the convolved windowed output at the end. The circuit we see in the middle is how a typical quantum circuit is designed. When we say an algorithm, it more or less means that we designed the circuit. So if you see such a circuit, it's just how quantum algorithms or quantum circuits are displayed for ease of comprehension. Once we have the convolved output and we rectify the window norm and the filter norm, we have the correct output, the convolved output. Now we perform the same for the various windows and we have a bunch of quantum windowed outputs. Now in this case we have the option of just classically overlap adding them, and we have the classical post-processing, and we get the whole signal at the end. This is an example of quantum reconstruction algorithm output. As you can see, we have a fairly faithful output here. Two questions we need to address. What about zero state? Given that we can't have a zero state because of the L2 normalization condition, we simply ignore them and we have to classically process them. And what about negative amplitudes? To address that, again, we have the option of just using a DC offset. Here we show the output for our simulations for a large signal. This was implemented in Cascade, and we show how quantum overlap add performs against a regular classical overlap add which we did in NumPy. The filter length, which was the sync filter, was n equals 8 in this case, and we have a fairly faithful reconstruction. Now we discuss our second subroutine, which is filter as a unitary gate. Earlier the filter was a register. Now we give an alternative where the filter is a unitary gate rather than a register. So in this case we won't be amplitude encoding the filter as such. What do you mean by unitary gate? Well, it just means that it's a unitary matrix. The circuit you see in front of here is nothing but a linear algebra equation, so to speak. We start with a column vector, we perform operations on it with matrices. In this case, we are bound by the laws of physics to use unitary matrices. And to perform filtering or quantum convolution in the frequency domain, we need to have a diagonal unitary gate, which is not a straightforward thing. So we have to deal with how we can design a diagonal unitary gate. We employ a technique known as the block encoding, which is to embed a non-unitary matrix into a much larger unitary matrix so that we can perform those non-unitary operations in a quantum domain. There are two types of block encoding: linear combination of unitaries and matrix access oracles. There are others, but for our case we are using the matrix access oracle, and the circuit is shown here. This is an illustration of how we do this. We start with the filter vector, we perform QFT on the filter vector, and we embed it into the much larger unitary matrix. We see that the green box here is non-unitary and it's a diagonal matrix, and this green box is what we are interested in and which we want to act on the quantum windowed state. So to accommodate the rest of the elements of the blue box, we have something known as the ancilla qubits, which we can see below the diagonal gate down in the circuit. The ancilla qubits is there to accommodate the rest of the entries. An illustrative output of quantum convolution algorithm where filter is embedded as a unitary gate. For this to happen in real time, we actually had to pre-process the block encoded matrix beforehand, because it's time consuming and memory exhaustive to do it in real time. But if we do it beforehand, it's fairly simple to do the rest of the things in real time. We see that when we compare the quantum convolution output as against the NumPy convolution output, that is the classical convolutional algorithm. The results are coincident and there isn't any difference at all. Third and final subroutine of our framework is the quantum overlap add circuit. Earlier I showed you how we actually classically overlap added the output, but we have the option of doing it in quantum domain as well, which we discuss here. The quantum overlap add subroutine we designed is inherently a probabilistic algorithm, and the circuit is shown on the right side here. For n qubit window, we need at least n plus 2 qubits for. Let's break down the exact operations in a quantum overlap add circuit with a 4 qubit example. We start with two convolution output arrays AIs and BIs, and we zero pad them to a power of 2 if it's not already. Now the ancilla qubit, in this case the Q3, actually doubles the length of this new vector, which we can see as another zero padding. This is the encoding step of the whole subroutine. Now we perform a splitting of the two convolution outputs into appropriate locations in the column vector, as shown here with a C NOT gate, that is a control NOT gate, which we label as the split operation. Now with a proper controlled permutation matrix, which moves around the coefficients of the column vector according to our needs, which we label as the slide operation, we have the output at step 5. We in this case we just move the BIs by 2 units, so to speak. And finally, with an Hadamard operation shown here as H gate in the circuit, we have actually performed the sum and difference. As you can see, the first half of the step 6 gives us the sum of the two convolution outputs, while the second half gives us the difference. And finally, we measure the ancilla, that is the Q3. When ancilla is measured as 0, we have our overlap add as the quantum state on the remaining qubits, which is our output at step 7. The probability factor, or we do have a probability factor for no square root of 2 before this, which we have to rectify manually with classical post-processing. This is an example of overlap add circuit output where the overlap add is done with the quantum circuit we show. We do see a phase difference, but if we undo that, it's coincident with the NumPy version. Now we show the full quantum reconstruction algorithm. We start with the classical windowing, we then encode it. There we have the option of either encoding the filter as a register or filter as a unitary gate. Once either of them are performed, we perform convolution and we get the quantum convolution output. Once that's done, we actually get a classical output. And for the quantum overlap add subroutine, we have to re-encode this classical data into a quantum state. And we perform the quantum overlap add to arrive at the final whole signal. Instead of re-encoding the classical data, there is the option of actually using the convolution output in the quantum domain directly to perform the quantum overlap add. For that, we can use something known as a QRAM, which stores the quantum state temporarily, which is similar to how a RAM works. But there are two challenges in this regard. We need 2 copies for each window convolution output, and different window currently has different norms, which is tricky to actually rectify. This is an active problem we are currently working on. That's the end of our presentation on our work. This was a brief overview of our paper. The paper actually delves much deeper into the nuances and details which I couldn't discuss here. Thank you all for listening, and I thank the organizers of ICASSP for this opportunity.